Okay, so in this assignment, we're working on a regression problem, and our data set is a diabetes data set from the scikit-learn toy data sets. And taking a look at the description of the data, we can see that we have 10 features, including age, sex, body mass index, blood pressure, and so on. And we have a target value, which is defined as a quantitative measure of disease progression 1 year after baseline, based on the scikit documentation. And moving on to the info of the data, we see that all our features and targets are type floats, and we have 442 rows of data. We can see all the ranges, means, maxes, and everything here. We can also see the histograms for all of them, but what is more important is the correlation between our features and our targets, which here we can see that the highest correlation is 0.59 for body mass index, and followed by 0.57 for S5. Based on documentation, S5 is possibly log of serum triglycerides level. And so because of the uncertainty in that definition, and the fact that it's slightly lower than this, I decided to focus on body mass index for my stratified sampling. So I did the stratified sampling by dividing body mass index into 5 bins and distributing them evenly in both the testing and the training sets. We set aside a testing set of 10% of the data, and we end up having 4 bins for our stratified sampling in the test set because the number of the 5th bin data was too small, too little to be assigned to this 10%. Okay, so finally getting to the training section. We started with training 5 initial algorithms, including linear regression, ridge regression with L2, polynomial regression, 2 different degrees, and nonlinear regression, in this case, SVR, and an ensemble model, in this case, random forest. And for our accuracy, we decided to consider root mean square error and R-square. We also applied a few other algorithms, which I'd like to add before we move on to the conclusion section and look at the comparison of accuracy between different algorithms. And these additional algorithms were, first of all, XGBoost, which is another nonlinear ensemble model. And then we had 2 deep learning algorithms at NLP and a neural network. And eventually, we did some cross-validation for the ridge regression and for the XGBoost. And this table at the end shows a comparison of accuracy metrics for all of these different algorithms. So to compare our linear and nonlinear algorithms, we can see that, first of all, root mean square error is better when it's lower, and R-square is better when it's higher and closer to 1. And in this case, we can see that the best models before applying the cross-validations are our 2 linear models and to some extent our deep learning models, even though they're still slightly lower in terms of accuracy. And the nonlinear models didn't really work well, especially for polynomial, both degree 3 and degree 5. We can see that R-square is negative, which is far away from what we want, and it's actually terrible. And the root mean square error is quite high. So let's forget about nonlinear ones for now and apply cross-validation on our ridge regression. So for ridge regression, we started with finding an optimal value for alpha, which is a hyperparameter in this case, and we found this number, 0.3. So we went back to the regression and changed the default alpha number, which was equal to 1, into this new optimal value. And our accuracy metrics improved, for example, for R-square from 0.51 to almost 0.6. And we also tried improving our XGBoost regressor by playing around with its hyperparameter, which in this case was the max depth number. So the default max depth for this algorithm is 6, but then we changed it to 2, and we observed that this optimal alpha value gives a better value of 0.53 for R-square compared to 0.43 for the default depth. So all of this being said, we can kind of conclude that our linear models are functioning best in this case, and our cross-validation helps improve the models slightly. However, these accuracy metrics are still not as good as expected, and my guess, and based on my research, and my opinion, is that it's because our data set is a weak data set. We don't have too many rows of data, um, and also features probably are not defined, like are not meaningfully correlated with our targets, or our target is not properly defined. So this is resulting in a not very perfect um, training in this case. Thank you for listening.